If you think way back to the Dalton solid sphere model of the atom, it said basically that all the atoms are different, but there's nothing that makes up the atom. The atom is a billiard ball. You might have an 8 ball, you might have a 6 ball. The balls may be different because of that, different colors, whatever, but in the end, there's nothing that makes up the ball. Okay, there's nothing different inside the 8 ball than there is inside the 6 ball. Then we went to the Thomson-Reisenbund model of the atom, electrons floating around in a sea of positive charge. Then we went to the Rutherford planetary model of the atom. Okay, it came from the gold foil experiment or the alpha scattering experiment, where the atom consists mostly of empty space with a small, dense, positive nucleus in the middle of this atom with the electrons orbiting around it. And then we went finally to the Bohr model of the atom, which made some refinements on the Rutherford model of the atom. Rutherford said that the electrons can orbit around the nucleus wherever they want. Bohr said they orbit around the nucleus, but not wherever they want. They have to orbit around the nucleus on specific levels. And each of those levels is characterized by a specific amount of energy. In a little while, you're going to see a diagram that's going to show the energy of these different levels. The second thing he said is that electrons, as they orbit around the nucleus, experience an acceleration, a centripetal acceleration toward the center of the circle. And according to Maxwell, they should emit EMR. This is according to that question on the quiz, or the practice question set that we had earlier, right? They should emit EMR, but they don't emit EMR. Okay? If they did, then the electrons would lose energy and spiral into the nucleus, and the world as we know it wouldn't exist, because there wouldn't be any electrons orbiting around, and there wouldn't be any chemical reactions as a result of that taking place. We call it a stationary state. The electrons are not emitting EMR. It's as if they're not moving. It's as if they're stationary. And finally, electrons can make transitions from high levels to low levels. In that case, they give off energy, always in the form of EMR. But they could also make transitions from low levels to high levels. In that case, they have to absorb EMR or some other kind of energy that's usually electromagnetic radiation. Yesterday, I showed you these 3 diagrams. These 3 diagrams, the first one shows us a reference diagram. Nothing to do with electron transitions per se, but rather just here's what happens when you have a hot solid. What was the key letter in this again? H, right? Hot solid, hot liquid, hot gas under high pressure. The key letter was H to remember the difference between high pressure and low pressure there. Hot gas under high pressure, hot solid, hot liquid, generates, well, if we were standing right here, what would we see? White light. We would see true white light, all the colors of the rainbow. But when I shine that through a prism or diffraction grating, it splits up that white light into its component colors. Because it's true white light, it would be all the colors or a continuous spectrum produced there. That's our reference diagram. We're going to compare our third diagram to that in just a moment here. Now, let's go to our second diagram. In our second diagram, we have a hot gas, but it can't be under high pressure because it produces something different. So rather, it's under low pressure. Hot gas under low pressure. What would we see if we were standing right here? It would appear to be white light. It wouldn't be true white light because it wouldn't consist of all the colors, but it would appear to be white light. When I shine it through a prism or a diffraction grating, I would see that apparent white light split up into its component colors. But you'd notice that that apparent white light wouldn't consist of all the colors of the rainbow. Rather, it would consist of a red photon and an orange photon and a couple greens and so on. What do each of those photons correspond to? What do each of those colors correspond to? These are electron transitions. These are photons that are released as a result of a transition of electrons from a high level to a low level. So from level 5 to level 3, from level 2 to level 1, from level 3 to level 2. Each one of these photons is released as a result of a different transition. Now, we go to our third diagram. We're back to having our hot solid, our hot liquid, our hot gas under high pressure, only for purposes of generating EMR. We need all the light. We need a continuous spectrum here. We shine that continuous spectrum through a prism or diffraction grating, and look at what we end up with, a continuous spectrum. Go figure. But if we introduce a cold gas into the mix here, the cold gas will absorb EMR. Remember, hot things give off, cold things absorb, right? When you're warm, you give off energy. When you're cold, you need to absorb energy. This cold gas absorbs photons. If we were standing right here, we would see white light. If we were standing right here, we would see white light. If we were standing over here, we would see the rainbow, the continuous spectrum, minus certain photons. A photon has disappeared because it was absorbed by an electron to make a transition to a higher level. Another one has disappeared. A couple more have disappeared, and so on. What do you notice about those two gases, the hot one and the cold one? They've got to be the same, right? This is a fingerprint. Okay, this is a fingerprint of the element. Every different gas gives off a different spectrum. And we can identify the gas, the unknown gas, based on what that spectrum looks like. Okay, if we see this spectrum, then we know that it's the same spectrum as this one. We know it's the exact same gas, except it's cold instead of hot. Does that make sense? All right. Take a look at this diagram. This is photocopied for you as well, but not in the same place that the other diagrams that I gave you yesterday were. This is in your example question booklet that I gave you on the first day of the unit. So I'm going to refer you to that so that you don't have to copy out this diagram. This is what we call an electron level diagram for hydrogen. Hydrogen normally has one electron present, right? But that electron can well, normally it would be on the first level, on the ground state, but it can switch levels. It can go to the second level, the third, or the fourth level if it absorbs energy. This would be the nucleus down here. And the normal place for hydrogen would be in the ground state or the first level. But if it absorbs energy, it can go to what we call an excited state. If it absorbs enough energy, then it can actually become ionized and leave the atom. We would call it a free electron in that case. I want you to notice a couple of things on the left-hand side of this diagram. We have energies on the left-hand side of the diagram, energies of these different levels. We expect to see unique energies for each different level, right? But what's a little bit odd about this is two things. One, the energies are negative as opposed to positive. And two, the energies get bigger as you get closer to the nucleus. And we kind of expect almost the energies to get bigger as we get further away from the nucleus. Let me give you an analogy here, okay? You're standing on the Earth. You're standing right here on the surface of the Earth. This would be analogous to an electron that has left the atom, a free electron. You've left the Earth. You're on the surface, okay? You're gone, out. You're not in the Earth. You're on the Earth. You're a free electron, okay? What is your gravitational potential energy right now relative to the surface of the Earth? Zero, right? We're going to define the energy of this free electron as zero. The free electron is like the person that's left the Earth, that's on the surface of the Earth or outside of the Earth. Now, let's dig a hole into the Earth and start climbing down. If we measure the potential energy relative to the surface of the Earth, what's it going to become as I climb down that hole towards the core of the Earth? It's going to become negative, right? Hence, the negative values of the energies on these levels. It not only becomes negative as you climb your way down towards the core of the Earth, it becomes negative and bigger because your height becomes a bigger negative value. So measured relative to the surface of the Earth, your potential energy becomes negative and bigger as you go down towards the core of the Earth. And that's exactly what happens here. The energy of this free electron is zero. It's on the surface of the Earth. But as you dig a hole and climb down towards the core of the Earth or towards the nucleus, the energy becomes negative and it becomes bigger. Now, we're going to do a couple of problems in just a moment here, but one thing that I want you to remember as we go through those problems is this. Okay, this is so fundamentally important. When you're looking at one of these diagrams, you will never, ever, ever use this number or this number, 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 or this number. You will always use this number and this number. It's never one number or the other. It's always the difference between two of those numbers. Got it? Never use one of those numbers, ever. Always use two of those numbers, find the difference when you're doing something with it. Sometimes it's just a matter, the question just involves subtracting the two numbers, done. Sometimes it involves subtracting the two numbers and then doing something else with it. But you're never going to do anything with just one of the numbers. If you do anything with it, it's going to be with two of the numbers. All right, let's take a look at example number 1 that's in the booklet that I gave you the first day of the unit. Determine how much energy is emitted when an electron makes a transition from the third electron level to the first electron level in hydrogen. Now, you understand that you can absolutely get a different electron level diagram for different elements. It's going to look the same. You're always going to find that this first gap is bigger than the second gap, is bigger than the third gap. The gaps get progressively smaller. It's going to look the same. The thing you're going to notice different about it is the numbers. The numbers for hydrogen would be different than the numbers for lithium or the numbers for sodium or whatever. But it's going to look, the structure of it is going to look the same. Okay, you get the biggest difference in energy between level 1 and level 2, and then the difference in energy between progressive levels past that gets smaller and smaller. We want to find for hydrogen the energy of the transition when an electron goes from the third to the first. So to do that, we're going to say the energy of the transition is the energy of level 1 minus the energy of level 3. The final minus the initial. Really, it's a delta E, right? A delta energy, a change in energy, the energy of the transition. From level 3 to level 1, so final minus initial is energy 1 minus energy 3. Energy 1 is negative 13.6 eV. Level 3 is negative 1.51. Notice what I've done there? Negative 13.6 subtract negative 1.51. When you do the math there, you end up getting negative 12.09 EVs. The energy of the transition is, well, technically when you give off energy, it's negative, but made it positive, it wouldn't be the end of the world. 12.09 electron volts. Subtracted, right? I didn't use 13.6 or 1.5. I used the difference between two levels, 12.09 EVs. Is that okay? That's not so bad, is it? It's just subtracting. If you have to use your calculator because of the decimals, that's fine. The second one says, an electron on the first level absorbs 12 eV. To what energy level does the electron rise? This is a good one. We absorb 12 eV. So we're on the first level, and we absorb 12 eV. Where do we go to? Well, if I'm at 13.6 and I absorb 12, what does that take me to? Negative 1.6. Negative 1.6 would be about right here. Oh, that's pretty close to level 3, right? It's pretty close to level 3. So where does this electron go? Level 3? Isaiah? It would go to level 2. How come it only goes to level 2? Because you can't go to level 3 unless you have enough energy to go to level 3. You're close, but that's not enough. You go to 7-Eleven and you're 5 cents short of having enough money for a large Slurpee. What do you come out with? A medium Slurpee, right? They're not going to give you the large, even though you're only 5 cents away from having the price, the amount for a large Slurpee. Okay? You got way more than enough than you need for the medium. It doesn't matter. You don't have enough for the large. We got way more than enough than we need to go to level 2. That doesn't matter. We're only going to level 2 because we don't have enough to go to level 3. Does that make sense? You need at least 12.09 to get to level 3. We only had 12. Oh, so close, doesn't matter. Next question, number 3 says, determine how much energy needs to be absorbed when an electron makes a transition from 2 to 4, and then what's the frequency and wavelength of the EMR that would need to be absorbed? Okay, so we're asked a little bit more on this one. From level 2 to level 4. We're going from 2 to 4 here. Let's get the energy difference right first. We're going to say E4 minus E2, final minus initial. E4 is negative 0.85 minus the 2 is negative 3.4. That gives us positive 2.55 EVs. Positive because it's absorbed. It becomes negative when it's given off, positive when it's absorbed. Although we're not going to lose too much sleep over the negative. Yeah, it's absolutely critical to put the negatives into the subtraction, otherwise you're going to subtract it wrong. But as an answer, it doesn't really matter. What about the frequency absorbed to cause that transition? Anybody have a stab at what we're going to do to find the frequency of photon that would be absorbed? Yeah? Good. E is equal to h times F, or F is equal to E over h. The energy is 2.55. What value of Planck's constant would we use here? 4.14. But if in doubt, what should you do? Use joules, but you'd have to convert that to joules as well if you were going to do that, right? I'm going to stick with the 4.14 times 10 negative 15. And as I do that, I end up with an answer of 6.16 times 10 to the 14 hertz. Is that a reasonable number? What kind of EMR do we expect to get? Yeah, infrared, visible light, or ultraviolet. This is visible light, right? So it's right smack in the middle of what we'd expect to get there. So absolutely. How would we find the wavelength? Yeah, you could say V is equal to F times lambda, or C is equal to F times lambda, or you could go back to this equation and say lambda is equal to HC over E. Either way, you end up getting 4.87 times 10 to the negative 7 meters. Notice what we use for energy here. What do we use for energy in this equation and in this equation? Not 3.4, not 0.85, but the difference between them. Always the difference between two energies, never the energy.